because logarithms have come up in the approximation of the harmonic series, okay, and they'll keep coming up when we analyze algorithms and see and apply our knowledge of analysis there. So we'll just do simple logarithm problems. Okay, these pop up in all sorts of exams, just MCQs. Okay, so it's a simple problem on logarithms. Also, in the complex analysis, the proper understanding of it will be needed to when we study complex logarithms there. Okay, so yeah, so first of all, before I say the problem, definition. Okay, so obviously I'm not going to give the formal definition, but what does, so, or rather my question is just if someone can describe in their own words. Obviously in the book you have definitions and such, but what is, or what does log b base a, let's say, or a base b mean? Yeah, if someone can describe this in their own words. This is very important because a lot of formulas of logarithms then start becoming very natural. So yeah, can anybody just describe this? Just in their own words, just as a phrase or something. What does this is a number, right? This is a number. What does this number, obviously there are some conditions and so on, but in general, broadly speaking, what does this number represent at the heart? Is that is the opposite of it, right? Yes, right. Yeah. So this basically, now this is something very simple, but so very often just this way of looking at it, just when you get confused with the formula, you know, there are a lot of formulas with logarithms. So just tell yourself this is, yeah, what power. So this is a number, okay, and this is the power. This is the power that you need to raise a to get b, okay? So you need to raise a to this power to get b. And this is usually given as an identity later on, but in fact, this is the definition. Okay. This is the definition. All right. So that was very trivial. Now let's come to the problem actually. Now the problems are also simple, but I just want to do them. How many, and these are some contest questions, some MCQ and some small contests. Okay. How many distinct solutions does log of, so here the base is interesting, and 4 minus 5x square minus 6x cube equal to 2 half. Yeah, let's try to do this quickly. Yes. So what should be the, maybe in general, what should be the first step naturally? Yes, right. So by the very definition, we get this, and then we need to just simply solve this. Okay. So has anybody solved this? Now this is a 4-degree equation, okay? So this is the same as sorry, 0 and -2. Okay, -3, sorry, -3. So are the answers, is this then going to be the solutions, or do we have to do something more? So what do you think? Is this okay, or do we need to check something else? Yeah. Yes, and more than just, yeah, that's obviously what theoretically that's what we need to do, but essentially we just need to check. We just need to check if this is positive at 4, right? If this is a polynomial p of x, then we need to just check whether p of 0 should be positive and p of -3 should be positive. If it is negative, then there is a problem. Okay. Otherwise all the steps are reversible, right? Except that this should not be negative. Okay. Yeah, this should not be negative, because obviously -3 will make this 0. So -3 will make this true. And so it will make this true. So what can we say? So actually we can say that we need not check anything. Here is the thing. Need not check anything, actually. So I would say wrong. Yeah, because this understanding is needed. Because very often we keep this as a thumb rule. Now, this is a point which is very useful from MCQ perspective, exam perspective, just for the timing and such. Might be a silly thing. Usually I don't discuss such things, but a thumb rule is given, right? That whenever you have these complicated equations, then whenever you get solutions, just substitute and check if it is working. People just say, right? Just substitute and check it in the end. And this is a thumb rule which is given, and it's very useful, because usually we don't have time to have a better understanding of the problem so that we can say. But just watch in this case. Just think yourself, right? This we have not squared anywhere. We have not done such things, right? We have not squared an equation. We have not introduced any possibility of any extraneous solutions. We have not done that, right? All the steps are, that's why I was putting these symbols, but then I also got a little, okay. I was putting the symbols, you see. So you would know that all the steps are reversible. And so this will be positive because all the steps are reversible, okay? And so we need not check anything. This is the answer. You can save time, okay? Now, so keep this as a habit whenever you are, and you will be practicing even for JEE or even for JAM or NET, whatever you're practicing, a lot of questions like that. You have to just make sure that when you're doing the problem, just develop this habit of whether the steps I'm doing are reversible or not. If they are reversible, that you need not check anything. Okay, you did not go back and check. So that is, I think that saves a lot of time in my experience also. So yeah, yes, or yeah. Yes. My point was that, see, my point was that like, let me just show you an example in the other direction where you do need to check, right? Suppose we have something like x plus 2 equal to 3x plus 9, and you want to solve this equation. Then a natural instinct is that you square both sides, right? So this implies that you have squared. And also, if there is any flaw in my argument, just because this is a thought of mine which is used to save time over years, but and this is, yeah, suppose you have this equation that you want to know the solution of, very trivial, but you square it, you get this. You see, this is not reversible. This implies this, okay? Just in very plain, simple terms, this means that if there is a value of x which makes this equation true, then it will also make this equation true. That's all it means, and that is correct. Yeah, if two numbers are equal, their squares are equal. That's trivial. But the reverse is not true. So I have not put this. Okay. So here, since the reverse is not true, there may be values which satisfy the second equation, but they do not satisfy the first equation. Okay. So there, since your step is not reversible, usually when you're squaring, and there, I don't know, I can't say all the possibilities, but you will know in the situation. Try to develop this habit of consciously understanding it. Don't just blindly substitute and check all the time. Okay, like here you will need to substitute and check. In fact, you will see that one of them will not work. Okay, because here if some solution is such that f plus 2 is negative, then you need to check. Okay, this is the thing that all of us are told. If you read a JE book also, they say in NCERT is just given as a rule. So, or even in whatever shoots, Shom's outline, whatever things you're practicing, you can see. Okay, so here it's not reversible, but look at here all the steps are reversible. If X satisfies this, if and only if X satisfies this, if and only if X satisfies this, right? Because you can just reverse the steps. If X satisfies this, you can just write this equation, right? You can just add 4 on both sides, just break it. You can understand. You can set, make it back, complete the square, make it here. And because we have only done reversible steps. Addition has a reversible, which is subtraction, and so on. Some simple stuff, right? All the steps are reversible here, and these are important. These are studied well in linear algebra also, whether your row operations are invertible, and that's why the solutions are preserved and so on. Very interesting theory comes up. But here it is similar, but in any case, you see, and it's all reversible. So we don't lose anything. So if -3 satisfies this, then it will satisfy this, then it will satisfy this, which is by definition this. So you need not check again. If you have along the way developed this or seen this, that it's reversible, or once you just have to develop this habit, it just becomes very natural. You do not have to even think. Okay, this is a very minor thing, but it can help you. All this, is it clear to everyone what I'm trying to say? It's something very silly, but okay, all right. So yeah, that was a very simple problem. Let us now do a slightly more interesting question, which is a contest question. I think this is the AIME question. So it's a good, let's see. But we'll do this. Maybe after class, if people find it very easy, you can tell me. So I'll not do these questions for next time, but I'll try to do at least a few. Yeah. So this question is AIME, I think 2019, but let us just, what is the question? Let's see. Yeah. So, yeah. So here is the thing. All logarithm. Now this for them was more verbose, but I have just made it like this. Just rephrase it. All logarithms whose base is not specified. Okay, let's see. Not specified is assumed to have base b. Like in math, in calculus and analysis, is assumed to be e. In computer science, it's assumed to be 2 for very clear reasons. Okay, but we'll go into that later. Okay, specified is not specified is assumed to be b, some b. Okay, whenever the base is not specified, and b is bigger than or equal to 2. Now you can think why this condition is given, but maybe that's not needed to do the problem. Maybe. Okay. Now the following equations are true. Following equations are true. This is 3 log . So this is very different from the kind of problems I usually do, but I realize that I should, do these kind of questions a bit. So we'll see, and then I'll take feedback later on and not do it if it's too easy. Is equal to 54. Yeah. So these two equations are given to you, and it's given to you, and sorry. So I should not say the equations are true. The following equations polynomial equations have one, okay, has one solution, has a single solution x bigger than 1. Okay, now all this thing, we now need to find that in that alien civilization or whatever, what base are they using, or some context in what bases are being used. Find the base. So remember that we do not have to find the solution. Okay, you may find a solution, I'm not saying, but we're interested in the base. Maybe you have to find a solution in the process or not, but the base is what we are interested in. Yeah. Assuming something, yes. So this log x stands for log x base b, basically. Yeah, the base is b. That is what we need to assume. And eventually we want to figure out that b. And it is given that these equations have one solution, maybe that, and it's greater than one. So that's another piece of information. Come on, we need to do this fast. I mean, you guys should do it fast, because these are the questions which have to be just done very fast. Yeah, so how do we write it? Okay. Okay. Okay, can you break that down and say that in? Oh, okay, yeah, that's the basically you're just using the definition. So yeah, so you see this number is 54 means that log x, which is the base to the power 54, is x. Okay. Okay. You want to put this in the first equation where? Here? Okay. So then, but you want to, instead of x, you want to make it log x to the power. Okay. So it becomes 27. Okay. Okay. Does it simplify the situation? I think, yes, the power can be brought down, right? So this will become, but then this, but we should have maybe just kept this like this, right? I'll keep both now. You can see which ones you like better. Right. Yeah, this one is better. This one all is in the same language, in the same way. So yeah, this one is a more. Okay, so then what do we do next? Yes, but we do not, yeah, right. But we don't know the base. Yeah, but then it is easy from here, right? You can just, you can put this here, right? And then you will know log x, and then you can know, I don't know, yeah, let's do it. Don't know. Yeah, so what should we do? Let's think. This is what we have. Well, I'll wait for you guys. Yes. Which one? This one? So how can we write it? Log x is equal to, okay, so you use that. Okay, so in this, and so this becomes x to the power 1 by 54 equals 56. And this is 84 by 54 log x is equal to 56. Okay. Then we can find the x, right? We have this equation also, and we have this equation also. So you can, yeah, you have the x, so you can find the x. So yeah, find the x, then find b. Then you can find b very easily. Please complete it. Okay. See, it's a very simple question. Just you have to. Yeah. Sorry. Yes. 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 No. No. So in this, so in this log x, he's putting this equation, right? Log x equals to x to the power 1 by 54. Right. So instead of log x, he's writing 1 x to the power 1 by 54. Okay. And then simplifying. Okay. Yeah, then just simplifying because 1 by 54 comes down outside. Okay. Yeah. Okay. Yeah. So please try to do this on your own. And if you need it, you can revisit this and check, but otherwise try to finish it on your own. Okay. All right. So now let's come to the actual questions, actual thing that I wanted to do today. Yeah. So what we have looked at so far, okay, have been infinite sequences. A little bit, infinite sequences. In what form have we looked at them? Okay, we have seen them for those who were there. Otherwise, you can also understand. Now, in the form of partial summations, right? Because initially we started with infinitely many numbers, and we're trying to give a notion of summation of infinitely many numbers, right? We are trying to give a meaning, give a sensible meaning, okay? Give a meaning to addition of infinitely many numbers. I mean, this is how mathematicians will put it. Computer scientists may put it as we are trying to understand what is the behavior when larger and larger number of numbers in a infinite collection are getting added, right? For n equal to 1, n equal to 2, n equal to 1 million, n equal to 10 to the power 10, n equal to so on. Now, what is the behavior? We want to give a meaning to this addition of infinitely many numbers, or we want to capture the behavior of addition of infinitely many numbers or larger and larger number of numbers. We want to capture this behavior using one number if possible. Yeah, we want to use one number to, and this is the limit, we'll define it clearly, but want to use one number to capture the eventual behavior if possible. Sometimes one is not, then we come to a concept called limit points, okay, which we will also do, capture the eventual behavior. And we'll yeah, let's go on. Eventual behavior using one number if possible. This is one way in which we can see. So what have been our things? We have been looking at things like hn, right? And if you want, you use one number or extended number like infinity. If you want to use one number to describe these summations, hn is summation from 1 to 1 by n, right? And you want to use one number to describe this that best describes it. That number is infinity, right? That one number that describes it is infinity. As n tends to infinity, as n becomes big, this is infinity, right? If you are looking at something like a geometric progression, then you know that the answer is 1 if it's half and so on, right? Otherwise, if you're looking at this, well, this should be gn plus 1, right? Then the gn plus 1 is, if you want one number to capture this, the behavior of this, then it is 1 by r minus 1. That is the summation formula of the geometric progression. We had even proved it geometrically, staying true to the, oh no, we didn't prove it explicitly geometrically. I gave it in the test, but then I never discussed. I think only 2 people were able to do it. But in any case, that doesn't matter. I think it's 1 minus r. Okay. In any case, we had shown an algebraic proof. So yeah. But the geometry proof is good. It uses the idea of homothety, which is nice for those who have not encountered it. But in any case, this is the thing. Now, what does this mean? What does it mean? What does this kind of thing mean? Well, we have described it. We are trying to say that this summation, yeah, this summation, or we look at the sequence of partial summations, right? The sequence of partial summations is best described by 1 minus r when n becomes very big, right? What do we mean by that? Best described. It means that given any error greater than 0, any epsilon greater than 0, there is some n naught, okay, such that g n naught, meaning that adding up to the n naught term minus this number which we are treating as the best description is less than epsilon. Is this okay with everyone? Yeah, that's what it means, right? For the summation of infinitely many terms to be 1 minus r, yeah, we are basically trying to say that this summation gets closer and closer to 1 minus r as n becomes bigger and bigger. Now, closer and closer means that as close as you want. And so, okay, if you are claiming that, then I'll throw an epsilon at you, and you need to produce an n naught. Okay. Now, obviously, this is not completely correct, but it works out. But let me first say why it is not completely correct. Okay. This is not completely correct because when we say that this thing gets closer and closer, this summation of terms, more and more terms, gets closer and closer to this number. This means that, well, this should mean that given an epsilon, there is a point after which this summation remains epsilon close to 1 by 1 minus r, okay? Remains close to 1 minus r by less than epsilon, right? This should translate as not just n naught, if there is some n naught such that for all n bigger than n naught, this should happen. So it's not just that some n naught you find, and for that the distance becomes less than epsilon. No, that is not enough. You must find n naught such that, or maybe greater than equal to, you must find n naught such that this happens. And not just this, but beyond this also, the summation and the partial summation and the limit, or the summation of all the terms, or the best description, whatever you want to call it, they remain close. So it's not just you go close and you jump out, then that doesn't make sense, right? We had seen examples, simple stuff, right? We had seen examples of that. But this must also happen for beyond that. Yeah, for the terms beyond that also, this must happen. Is it clear to everyone? Please just have a look at it. We had done this as half square using that example, but here I'm just replacing that by r. Is it okay with everyone? Is there anything that I should repeat here? Okay, all right. But because G1 is less than G2 is less than G3 and so on, right? This is a feature that you can all understand here, right? This is a monotonic sequence. This is where the, game becomes interesting, and we go into monotonic sequences, and then the combinatorics comes in. The same idea, pigeonhole principle that we used last time, we'll be using again to develop the necessary analysis. And developing it like this, you see, then you will also understand that what are the true criteria needed, okay? Like if you directly land up with the theorems in analysis, then it's not very clear what part of the theorem is combinatorial, which means that it will also be true for just any set with order or any other things, with numbers which are ordered by division, okay? Or is it only going to be true in the real analysis, real numbers? Not very clear if you directly see it in a Rudin book or in a book, or in a calculus or analysis book, right? But if you see it in a different way, then you will know that, okay, this is the combinatorics part, this is the analysis part, and so I can generalize this like this, I cannot generalize this, and so on, so on. So it's very important to just look at the straws of the matter. So this is the thing. But yeah, here let's pay attention, okay? Because this is an increasing situation. Because it's an increasing situation, this implies this. Is that right? Yeah. If for some n naught, so let's see. So here let's say you have let's just take one. Let's take r equal to half. This is very simple, but just enough to understand. I suppose you can already see it, or the most of you can see, but I just want to isolate this point. Okay. Let's put r equal to half. Right? When you put r equal to half, then you know that 1 is where the entire thing is going to go, right? Now let's say you put epsilon equal to 1 by 100, right? 1 minute. Something in the, yeah. 1 second now. Yeah, you put epsilon equal to 1 by 100. Now the question is, how many terms do I need to go to? Okay, how many terms do I need to go to? So if you put this, then I want to find the n naught. Let me just do one thing. Let's not make it very cluttered. See, I want to find the n naught such that the gap becomes less than 1 by 100, right? And then you will see, and you can just see it, that beyond that also it will work. But we just want to actually see that maybe more explicitly. But what should I do? Let's move this. 1 second now. Okay. What we want to say is, yeah, you put r equal to half and you have epsilon equal to 1 by 100, right? What we want to find out if in this picture is, we don't want to find out, but we want to show that there is some, yeah? But let's just write it constructively, okay? We want to find n naught such that 1 minus, hold on. I started with 1, right? No. In any case, I can't start with 1, we'll start with half. Half plus half square plus 1 by 2 to the power n naught. This difference, or I could have just put mod, and in any case, this is already positive, is less than 1 by 100. We know that such a thing will exist because we know that this summation gets closer and closer to 1. And it remains close and blah, blah, blah. We can just see it. Yeah. So we know that such an n naught exists. Everybody agree with this. Yeah. We know that such an n naught will exist. Can anybody just guess some n naught which will work? If you can. This is not important for our discussion, but how would you actually not find, but maybe guess the n naught? Or just give an estimate of what that n naught, what n naught will work? Some n naught that will work. Anyone has thought about such thing? Like, how far do I need to go so that the difference remains less than 1 by 100 from 1? Any quick answers? 7 or 8 terms would be enough, right? Just think about this. So let's not, yeah, just think about, yeah, this is not, so don't, okay, you can use some formula again. You can use some integral method if someone knows, or you can just take the formula of geometry progression, right? But just think from the process so estimate the n naught. Okay, but we know that such an n naught exists. So if we know that the n naught exists, then basically my point is that if you consider this 1 minus 1 by 100, and not this, I'm making this very like a baby version, just doing it like this very explicitly, but just so that we can understand this once and for all, because soon we will be doing rearrangement of the series and showing if the summation remains the same or not. No, because we know that 1 plus 2 is equal to 2 plus 1. But when you're adding infinitely many terms and shuffling, then what happens? So then shuffling or doing a permutation of infinitely many terms and what happens and so on. So it's very important to understand it very clearly. So it is this, and we know that there is some n naught which comes here. So there's some n naught such that g n naught. G n naught is addition up to n naught, right? It's, you guys know it. Yeah. Okay, it comes in that in that bar. That's what it means for the distance to be less than. Yeah. Okay. But see, we needed that for all n after that point also that it happens. But then because g of n naught plus 1 is bigger than g of n naught, you need not do anything. You know that automatically it's going to be here. It will not cross 1 that you already know, so you can forget about that. It will not cross 1 that we have shown to begin with. Yeah. And then it will. So my point is that if you can find some n naught that for which the difference is that is this less, is less than 1 by 100, then that's it. For the rest of the terms after that, you need not check. Okay, so the one actually is called the supremum. Okay, but let us not go into that. It's the analysis part which I'll be doing once we are done with the combinatorial part of this topic. Okay, we don't need to stuff all the definitions right now. Yeah. So this was my point, that the just knowing that n naught is enough. Once you can find an n naught for which the gap is less than needed, then that's enough. Okay. And now you can understand that. So now you can understand one thing, that increasing sequences or decreasing sequences are very good. For decreasing sequences, a similar reasoning will work, right? So now if instead of partial summations, instead of, well, every sequence can be seen as a partial sum, but that's rather contrived. Sometimes it's needed to do problems, but yeah. Instead of partial sum wala sequence, but that was a kind of sequence which is naturally occurring, right? That is a kind of thing when you pick up small numbers and you add and so on, then these questions come up naturally. But yeah, but that's not true that it only comes in this way. There are many ways, many situations in which this sequence is common, which are not through partial summations in a natural way. Instead of partial summations, yeah, instead of partial summations, if x1 less than x2 less than x3 dot is any infinite sequence, yeah, if it is any infinite sequence which is monotonic, so I've just written it like this. This is what is called monotonic. Now monotonic can also mean not decreasing, okay, but this is what is called monotonic, okay, and it is bounded, okay, and bounded. Now bounded, you guys know, I have defined it. Okay, just make this term bounded. Bounded means that all the terms are less than something. If it's unbounded, then there's also picture is also clear. It just goes to infinity. This clearly goes to infinity. Then the question comes on how fast it goes and so on. If there is a good function that you can use, but that's there. Okay. But if you have a monotonic and bounded sequence, okay, so there is a bound, which means that all of them are less than m. Okay, so all xn is less than m for all is for all n. Okay, then you see for this kind of sequence also, it's very I mean, I will not say it's easy to describe one number which the sequence goes to. Okay, it's not easy to find. Okay, I should say it may not be easy to find that one number where the sequence goes to. Okay, but it is easy to describe it mathematically. Okay, at least the way the system has been built. Yeah, what do? We just take, so this is an upper bound, right? We take the least upper bound. Yeah, take the least, roughly speaking, we'll describe this more clearly. This is what is called supremum. Okay, we take the least of all upper bounds. Well, why does such a thing exist is not totally clear, and that's an axiom that has to be put in, but we'll see that much later. Okay, we take the we take the least of all upper bounds, and once, so basically I'm saying that if you take the best bound, right, that's it, that's all you need to do. So if x1 is here, x2 is here, x3 is here, and m is a, you know that there is a bound. Okay, then if there is a bound, it means that all these terms are going to eventually stop somewhere. So the place where they stop, that is a limit. That is what you can, that is a number that you can use. Now, if there's a number there, so it turns out that there is no number there sometimes. If you're only looking at the rationals, sometimes you may not find a number there. Then you have to extend your rational system. And that is how the real numbers come in actually. Okay, that's the definition of real numbers. Yes, that's actually how it comes in. Yeah, but in any case, we don't need to worry. We can assume that there is such a thing already there. Okay. So my point is that from partial summations, we can draw an analogy and generalize this thing to, no, these are just ideas, okay? But the whole point of this discussion is to appreciate how important monotonic sequences are. Yeah, if a sequence is monotonic, then a limit is almost guaranteed. Okay, it's almost guaranteed. But see, this is not just for monotonic sequences. We will see that if you have a sequence, if it has a monotonic part also, okay, then that can also sometimes be enough. Okay, so if this is clear, I'll just erase a few things. Then going. What I'm trying to say is that let's try to view this in a slightly different way. Okay, this increasing sequence. The sequence is still increasing, but you can sort of try to draw it in a more more two-dimensional way. That is, this is 1, 2, 3. Just drawing it very close. So say 7. Okay. Now, if your sequence is monotonic, so what I'm going to do is on the y coordinate, I'm going to plot the value. Okay. So this one is x1. Okay. This is x2. If it's monotonic, and it is bounded, okay, and these are very powerful methods. Okay, looking at a sequence as part of a function, it can really, help you, because we have the theory of derivatives and such to check monotonicity, and so all of them play out very nicely in the end. Okay, from problem solving perspective and so on. Now this sequence is monotonic and it is bounded. So if it is bounded, it kind of has a maximum you can think of. Okay, it's kind of a maximum. It's not a maximum. It's never a maximum unless it's constant eventually, but it's kind of, where it is, going. So you see, then the sequence goes, let's say it goes here, right? So, I mean, yeah, that it never goes above that, obviously, but it gets closer and closer as the terms increase. Yeah. So it's the same picture, right? But this is a one-dimensional version of it, and this is the two-dimensional version of it. This is the, maybe this is the maximum max of the sequence, which is theoretically speaking is wrong, but you can understand. Similarly, you can see for a decreasing sequence, right? So this is the situation. When this is a maximum, then you take this, and then, then you see it gets closer and closer to this red line. And so given any epsilon, any error, eventually all the terms of the sequence are in it. And that's only because one term is in it, then you don't need to check the rest. Yeah. But by the fact that this red line is the maximum or the least of all upper bound, this will work. So monotonic sequences can be described by a number. And those are the numbers which are used to extend the rational numbers. Okay. But the situation is not just for a monotonic sequence. Okay. Sometimes what happens is some arbitrary sequence will have a monotonic part, and that will drag the sequence to a limit. So what can happen sometimes is, and this happens very, very often, is you have a sequence which is like this, but it's oscillating, but then its oscillation is going lesser and lesser, right? So it's not monotonic, but there is a monotonic part, and that or maybe there is a better monotonic part in between somewhere. See, right? Then this part, its limit. Now, if we can find a monotonic part in a sequence, right, then you know that it will have a limit. That part will have a limit. That part will have can be described by a number. Okay, and if there is a further condition, obviously we'll formalize these things, but if there is a further condition that this monotonic part drags the rest of the sequence along with it, then the whole sequence will have a limit. So this is the way we do it usually. We find the monotonic part of sequences, and then we prove that it has a limit. And if we have some other condition which kind of assures that all the sequence kind of gets, the spine is the monotonic part and goes in, right? And so the entire sequence starts having a limit, so we can prove it. Otherwise it would be difficult to prove. Okay, so this is essentially the idea in which we prove limits exist, so on. We prove it's monotonic, or it's can be split into two monotonic parts, or it has a monotonic prime monotonic part, and the rest of it just collects around it. These are the ways in which we prove that a large family of sequences which may not be monotonic still can be described very accurately, or as accurately as you want, by one number, if you're willing to go far down enough in the sequence. Okay, so monotonic sequences are very desirable. The point of the discussion was to convince ourselves that monotonic sequences are important. So naturally, we want to start looking for them. We want to start finding order in chaos. Yeah, a sequence is maybe a chaos, right? And then we want to see if it has a monotonic part. That is really what we are looking for. Okay, so is everything clear so far? Then we can move forward. Are there any questions? Yes. Here. Yes, so yes, so the monotony does not have to start from the very start. It can start happening from after some point onwards. Okay, but even here, from here, you can see a monotonic part from the start kind of itself. Okay, but it doesn't have to be from the start. Okay, it can start from a certain point onwards. Yeah, because eventually we are interested in what happens eventually to the sequence. Initially, anything can happen. Yes, so it need not start from the very start. Yeah. Okay, so now we want to prove this philosophical statement that monotonic sequences are abundant. And this statement can be seen in several ways. Even graph theoretically, we will see in the graph theory class also, or rather monotonic sequences are abundant. Or the way to put it in another way is that there is no true randomness. True randomness does not exist. Okay, there is, because if you try to avoid randomness, then the force that avoids randomness kind of has an order to it. So the complement, if there is randomness in one sense, then the complement becomes orderly. And that is a kind of statement which keeps occurring throughout mathematics. Number theory, graph theory, we'll see it very clearly in graph theory also. But here first we'll see it in the most barest sense, where we do not need any arithmetic, anything. Okay. So now, so for this, we want to have this. So if x1, now this is not monotonic, this is just a set of numbers, not even numbers, you just something where you can put a sense of order, but you can just assume that these are numbers. Okay, x1, x2, x3, x4, x5, s6, one second, so 7, and so on. This is just a sequence. Okay, so this is just an infinite sequence, and nothing else. Okay. So I was just thinking if that really works. Okay, anyways, it's better to see that after we're done establishing. Yeah. So if there is a sequence like this, okay, and it's not monotonic, okay, not monotonic, you try to draw it. Okay, try to draw it. You can try to draw it in a very random way. So this is, I'm plotting the values. Okay, the inputs are on the x-axis, meaning n equal to 1, n equal to 2, plotting the heights, obviously. This just what it is naturally, and so on, right? So it could be, you can try to make it as random as you want. Okay. Can we say anything still, right? And see, the point is, even when you are making this, right, you try to make this by avoiding to get a monotonic sequence. You try to avoid a monotonic sequence. So that's what you should try to do. Number one is try to avoid monotonic, I should say subsequence. Okay. Now subsequence just means part of the sequence, meaning that what's a subsequence? You see, I can take x2, x4, x5, x7, x100. That forms the subsequence, and so on, so on. I can that can be infinite. Okay, a subsequence just means that you just pick a part of the sequence in just the same order. Means terms should come next. I mean, the terms next term should be somewhere, down the line. Okay, so you have x2, x4, x5, x7, x100, x200. No pattern, just I1 bigger than I2 and so on. Okay, so try to avoid getting a monotonic sequence and also try to avoid getting a monotonic subsequence. Okay, you see here I'm not able to avoid because I'm getting this increasing part. Now if I try to avoid this happening again, I'll try to go down. I'll try to keep going down, but then I don't want to go down also. So then I have to go up. But then I don't want to go above this, and I have to go down. So you see, there is some problem. We were trying to create chaos in the increasing way, then the complement is coming in order. There's the order in the decreasing. You're getting something decreasing. Try to avoid that, you get something increasing. Okay, so do people feel that you cannot really avoid getting an increasing subpart that is infinitely long, or a decreasing subpart. If you avoid an increasing subpart, then you'll end up with a decreasing subpart, a decreasing subsequence. Yeah, is that intuitively making sense? If it is not, then also you should just say, because it is not such an obvious statement. That's why it's a theorem. Not straight line, but it is increasing. It's going up. The values are increasing. No, not really similar fashion, just increasing is it? Somehow increasing. Right? Meaning that this could be x3, this could be x10, this could be x100, but it should just be increasing. Yeah. And yes, the whole sequence can go up and down, but there will be an increasing part like this. Now, I'll formally define it, but you can understand what this roughly means. Increasing part means that there is okay, let's define it. There is xi1 which is less than xi2, which is less than xi3, and so on. This is a part, right? Where I1 is less than I2 is less than I3. So these terms are not consecutive, but they come one after the other. Sorry, that's the same thing. These terms are not consecutive, but they come after. I1 comes before I2, I2 comes before I3, and so on. Okay, just like you can see it in some. Okay, so my point is that you cannot avoid getting this. Okay, or if you can avoid getting this, then you cannot avoid getting a decreasing one. Okay, then you'll get a decreasing thing like this. Okay, let me just show why. Just if you try to draw, suppose you try to avoid getting an increasing sequence, increasing thing like this. Okay, so let's try to avoid an increasing subsequence. Okay, so how can you avoid such a thing? So basically, you don't to avoid getting an increasing subsequence, you don't increase, you don't keep increasing, right? So in a sense that you are here, and then you can decrease for as long as you want, but then you increase beyond the first term. Okay, and you've increased here. Now, after some happens, but after some time, you have increased beyond this peak. Now you don't want to keep doing this, right? You don't want to keep increasing. Means you can do up and down, but again, you don't want to again increase. This thing you want to stop, right? How does it stop? If you want to stop it after some number of terms, right? If you stop it here, I mean, this is the peak. You can't go higher than this, right? What does it mean? It means that, what does it mean? It means that now you try to, now it means that you don't want to go higher than this. So I want to avoid getting an increasing subsequence. I want to avoid getting an increasing part, right? Then you have to go down next. So there will come a point after that you can't really increase, right? So you have to go down. You go down, down. But then you are ending up with a decreasing part. So you'll say, no, I'll stop. Okay, if you stop, then you'll try to go up, but you can't go above this, right? So then you have to kind of come down. It means you have to stop, and then you have to come down, and then you see, then this will form a decreasing part, and so on. Okay, that is the sense that either you will get an increasing subsequence or you will get a decreasing subsequence. This is unavoidable. Okay, so I'm not proving anything today. Okay, think about it, try to frame an argument. Okay, try to first write what this increasing subsequence means. Don't try to do it yourself. That is the best way. Okay, think about, spend some time and think about it, do it yourself, and show that you will either get an increasing subsequence or you'll get a decreasing subsequence. Okay, and here is, this is slightly less combinatorial, but here is a more combinatorial version of the question. Again, try to do this on your own. This will also give you insight that if x1, x2, x3, and so on till x n square plus 1 is a sequence, okay, then either, or I'll just say, then there is a monotonic subsequence. This is a very standard question. It's some theorem of Erdos and Szekres, I think, I don't know how to pronounce it. There is a monotonic subsequence of length, but these two theorems are not the same. They're very similar, but they're not the same. Okay, you can think about it. Okay, subsequence of length at least n plus 1. These are not trivial statements. These are not trivial statements to prove, but think about it. Now, some of you may have seen this or may know the trick, then it's very simple for you maybe, but just think about it. And the idea will again be pigeonhole principle, the idea that we used earlier in the approximation of the rationals, which we have topic which we have stopped for now, because that becomes a little hard from there. So we'll not go there too much now. Okay, this. Okay, so this statement you understand, right? If you have a big enough sequence, if n square plus 1 terms, okay, very big enough sequence, right? Then there will be a part of length n plus 1. So it could be something like x1, x5, x7, you know, something like that, or you know, x11, x100, maybe till xn square. Maybe this will be an increasing part. If we show that something like that has to be there, or there will be a decreasing part, you can assume all the terms are distinct. It doesn't matter though. Okay, all distinct terms. Then non-decreasing will come in. Okay, think about it. Take some examples and try. Okay, think about, and these two statements are related. If you can try to prove one from the other, then that's also a thing. But I don't think one can do it, though it looks like that. But they're similar nature. Okay, so yeah, think about these things. This we will see more of in discrete maths. This is a very interesting topic to motivate poset theory and other interesting theory, lattice theory, anti-chain theory. Yeah, but yeah, think about these questions. Okay. That's what it is for today. So there was a question about permutation, but I'll not do it in this class. Maybe I'll do it in some other class. Okay, because that's a slightly advanced. It needs some, yeah. So we'll not do it today. We'll do it next time. So are there any questions? Okay. So if there are no questions, yeah. Yeah, let's do it now. Yeah, let's do it. Can you say the question? Yeah, let's do that question. So color the points. Yeah, the question was color the, yeah, let's do that question. Yeah, there was another question which I had given about approximating that the Q&A sort, but that's not easy to do actually. I realized that it needs some concept of continued fractions such. So don't bother about it too much maybe. Yeah, let's do this one. This one is a very interesting question. It has the idea of closer and closer wall idea. Let's see. Uh, color the points. Yeah, I'd made a mess while saying the question also. Color the points of R2. So there are points now. Do you want to color them with two colors? Yeah, you want to use two colors. Then let's say red and black. Okay, such that for any line, okay, so that no line is able to separate the color. Okay, no line can separate the color, so that for any line L, there is a side with 2 points of different color. Yeah. So basically, we want to say that so this maybe can be said as uniform coloring problem, right? So you want to color R2 in a way that given any line, it cannot totally draw a border between the colors. Okay, so it means that if you take any line, well, with R2 these two lines are already there, because what is this? Any line you draw, there will be on one side, in both sides actually, you'll get a red and black point on this side. So this line is not able to separate the colors. That's how the question is uniform color. So how do we do this problem? How do we establish the coloring scheme? This is also a graph in some sense. That would be a very strange way of looking at it. Yeah. If you draw two black lines, like this X and Y axis. Okay, and color. Yeah, so this may be a trivial, in that sense, trivial question. So yeah, if you color everything else red. Yeah, so then one black line, yeah, that works. Wait, shouldn't be so easy. Yeah, but it just works, right? Because yeah, maybe I should have made the question thought of better way. Yeah, this certainly works, right? Because if you take any line, yeah, it obviously works. Because if you take any line, if it's parallel, if it's not parallel, or you take as parallel, yeah. Take any line, then yeah. This is a very underwhelming. Okay. Yeah, this certainly works, right? Because no line can do it. So how can I make the question more interesting? Yes. So that's what it is, right? So therefore, any line it cannot separate, and it is not separating. One line is not separating, right? Two lines are needed. Right. Yeah. One line is not separating. We are needing two lines, right? So if you now take any line, if you take this line, it is not separating, right? Because you look at the above part, there is a black point and there is a red point. Take any line you see, yeah, not separating. So this is 1 minute, huh? 1 second. I think we can make the question more interesting. Yeah, but two lines, but you can understand that two lines are separating, right? The way this is done, right? The way this is done here, two lines are able to separate. Yeah. Yeah. So 1 second. So I want to say that find a coloring scheme such that any finite number of lines will not be able to separate. So 1 second. So you have a line, you take a point outside it, thing, then you can draw. Yeah. So I'll change the question such that any finite number of lines, any finite number of lines cannot separate the colors. I'll just describe this more clearly. Cannot separate. Yeah, this can be said, then we don't need more language about closed curves and so on. So any finite number of lines cannot separate. Or maybe any polygon cannot separate, you could say. Or what does it mean? So when I'm trying to say that when you take some finitely many lines, then what you end up is take some finitely many lines, you end up with a lot of chambers, right? So you have this chamber 1, you have this chamber 2, yeah, you have this chamber 3, 4, 5, 6, 7, 8, 10, right? And these chambers should not be able to separate, meaning that, you know, you should none of these chambers should be of a single color, right? None of the chambers formed, none of the chambers or the parts, you can understand, right? This is the part. This is the part, right? None of the chambers should be, or yeah, I can say, yeah, should be of the same color. Any finite number of lines you take, none of the chambers, so it will create these chambers, right? None of these chambers should be of the same color, because, or I should maybe say all of the chambers should not be the same color. Okay, but this will also work. You can find a color information. Okay? Because if all the chambers are like each chamber is of some particular color, right? Then it's like, you know, the colors are separated in those chambers and in the palette. But that should not happen. You need to color in a way that it cannot happen. Yeah. Now you can think about this. Then let's discuss this the next. Again, the idea, and then when you listen to the solution, or if you find it, you'll see this very, very simple. Okay. But yeah, let's see. Okay, let's think about this. Yeah, next time I'll